Welcome to the session on the normal distribution, review exercises. The objectives for this session are to review previous topics through exercises, namely, understand the model of the binomial distribution and calculate individual probabilities for the binomial distribution. Pause the video and have a go at these review exercises. When you are ready to view the solutions, press play. Let's take a look at the first exercise. Suppose the probability a baseball player makes a hit is 0.462. If the player bats 3 times in one game, estimate the probability that he makes 3 hits and that he makes no hits and that he makes at least 1 hit. So let's solve this. We're going to begin by creating a tree diagram. The player can either hit or not hit. The probability of hitting is 0.462. Therefore, the probability of not hitting is 1 minus this value, which is 0.538. And the same goes for the second time and the third time. Now that we have our tree diagram, let's calculate our probabilities. So let's solve part A first. We're required to find the probability that the player makes 3 hits. This will be the case if he goes down this pathway as highlighted on your screen in the tree diagram. So, since the probability of a hit is 0.462, the probability of 3 hits is 0.462 cubed. And therefore, plugging this into our calculator gives us that the probability of 3 hits is 0.0986. Now let's solve part B. We are required to find the probability that the player makes no hits. So let's solve this. If the player makes no hits, then he's going to follow this pathway as highlighted on your screen. And the probability of 3 no hits equals 0.538 cubed, which when plugged into our calculator gives us 0.156. And now for part C. We're required to find the probability that the player makes at least 1 hit. So let's solve this. The probability of at least 1 hit equals 1 minus the probability of no hits. And since we calculated the probability of no hits in the last part, we can plug this value into our formula or into our equation, as shown here. So we have that the probability of at least 1 hit equals 0.844. Before attempting the next exercise, we're going to take a look at some theory which will help us to solve it. In an experiment or survey, when carrying out a number of trials, a random variable x can be defined to represent the number of successful trials. The variable x can be modelled by a binomial distribution b bracket n comma p if the number of trials n is fixed, there are 2 possible outcomes only, the probability of success p is fixed, and trials are independent of one another. If a random variable x has binomial distribution BNP, then its probability mass function is given by the probability of x equals r equals n choose r p to the power r times 1 minus p to the power n minus r. N is sometimes called the index. P is sometimes referred to as the parameter. C n choose r equals n factorial over r factorial times n minus r factorial, where of course n factorial is n times n minus 1 times all the way down to 3 times 2 times 1, and 0 factorial is equal to 1. This is convention. Also, if the probability of a success equals p, then we can derive the fact that the probability of a failure equals 1 minus p, since of course there are only two possible outcomes. Now let's take a look at the next exercise. The random variable x is distributed binomially with n equals 9 and p equals 1/3. We are required to find the probability of x equals 3 and the probability that x is less than or equal to 1. So let's solve part A first. We're going to use the highlighted formula. And using this, we have the probability of x equals 3 equals 9, choose 3, times 1/3 to the power 3, where of course 1/3 comes from p equals 1/3, multiplied by 2/3 from 1 minus p to the power 6, which comes from 9 minus 3, or n minus r. So tidying up gives us this expression here. And tidying up some more, we have 84 times 1 over 27 times 64 over 729, which gives us 1,792 divided by 6,561, which is equal to 0.273 to 3 significant figures. Now let's solve part B. We are required to find the probability that x is less than or equal to 1. So let's solve this. The probability that x is less than or equal to 1 equals probability that x equals 0 plus probability that x equals 1. So plugging in the values, we have for x equals 0 this expression here, plus for x equals 1 this expression here. And tidying up gives us 2/3 to the power 9 plus 9 times 1/3 times 2/3 to the power 8. Which equals 11 over 3 times 2/3 to the power 8. Which gives us 0.143 to 3 significant figures. And now for the next exercise.
So let's take a look at Part A first. The probability that a randomly chosen member of an A-level maths class also studies A-level literature is 0.2. A random sample of 15 members of the class is taken. Suggest a suitable model for the random variable x, the number of members in the sample who are studying A-level literature. So let's solve this. There are going to be two possible outcomes, taking A-level literature and not taking A-level literature. The number of trials n is 15 because there are 15 members in the sample. The probability of a success is p. This equals 0.2. Therefore, x is distributed binomially with n equal to 15 and p equal to 0.2 as shown. And in this, of course, we're assuming each member is independent. And therefore, this is our suitable model. And now for Part B. We are required to use our model to calculate the probability that exactly 9 members in the sample study literature. So let's solve this. We have that the probability that x equals 9 equals 15 choose 9, since n equals 15 and r equals 9, times 0.2 to the power 9, since p equals 0.2 and r equals 9, times 1 minus 0.2, since of course 1 minus p is 1 minus 0.2, to the power 15 minus 9, which is n minus r. And this of course gives us 15 factorial over 9 factorial times 15 minus 9 factorial times 0.2 to the power 9 times 0.8 to the power 6. Which equals 0.000672 to 3 significant figures. This brings us to the end of this session. If you have understood its contents, you should be able to understand the model of the binomial distribution and calculate individual probabilities for the binomial distribution. Thank you very much for listening.